So next is going to be another application of light, and this has, actually now we're going back to light. So we did a little side note back into sound. So now we're returning to our discussion with light. So another property of light that we notice is that color actually relates to temperature. So what you find is that red light actually corresponds to a relatively low temperature, about 1,000 kelvins here. And as you go from red to blue, you find that blue light is actually a lot hotter, so 10,000 kelvins. So then for light, color relates to temperature. And the object that you use to figure out that relation is something called a black body. It's black because it absorbs all light, so that means that no light goes back into your eye, so it appears black. But on the other end, also, if you heat up a black body, it'll also send out all the different colors of light, and it'll appear white to you. This is something I forgot to mention, but when you combine all the different colors of the rainbow, you actually get white light. So this is an example of a model of a black body, which is something where light comes in and is trapped and it never leaves. So it would appear as if the light never reaches your eye. So this is a way to model a black body using an oven, which is pretty much an oven with a small hole. And just from those studies, we find an interesting observation that you can relate the color of light to the energy of light. So if you have an oven, let's say that you have two ovens. One of them is going to be at a low temperature, and one of them is going to be at a high temperature. And the ovens are going to have a small hole. So here, let's say that this oven is pretty cool. It's just warm. So what you're going to find is that the oven is going to glow red. So it's going to glow mostly red. And red is going to have a particular frequency. But then you can also detect other frequencies, but to a lesser extent. So there's going to be some orange. But there's going to be some green, but less. And there's going to be even some blue, but even less of that. So, and here, the fact that the oven is warm, you can relate that to the temperature of the oven or to the energy. And in the other case, if you have a hot oven, so here then the temperature is going to be high, so the energy inside the oven is going to be high. And what you find is that in this case, the hotter it gets, the bluer it's going to get. So if you analyze the light, you'll find that there's not that much red light coming out of it, and there's going to be successively more of the other colors. So there's going to be a bit more orange light, and there'll be even more green light, but there's going to be mostly blue light. So when things are hot, they glow blue, and when things are cool, they glow red. And blue light has a particular frequency, which I'll say frequency blue. And just based on that, we can have a relationship between the energy of light and the color of light. And the relation says that the bigger the energy that light has, the higher their frequency it's gonna have. So the energy of light is directly proportional to its frequency. So the bigger the frequency, the more energy it has. And also, a high frequency means bluer, or implies blue light. But we still have to add one more thing. So energy is measured in joules. Frequency is measured in hertz, so these aren't the same units. So we have to have a constant to make these two sides match, and that constant is called Planck's constant. And the value for Planck's constant is equal to 6.63 times 10 to the minus 34 joules times seconds. So these ideas were studied in the 1900s, and Albert Einstein actually used this to come up with a modern interpretation of what light is, and it's the idea that light is actually both a wave and a particle, like a billiard ball. So you can have a wave of light traveling, but if you zoom into it on a microscopic scale, you find that light can actually behave as little pellets or little balls of light. And those balls of light are called photons. This simulation is going to show us how Einstein was able to propose the idea that light can behave both as a wave and as a particle. So here what you're seeing is that you're shining a laser onto a sheet of sodium, and at first nothing is happening. And you can increase the frequency of that laser. And you can keep on increasing it. And if you notice here, sodium has a specific energy where electrons are stuck to its surface. And it was found that as soon as you increase the energy of the laser so that it was bigger than that value, so for example in this case here green, then you start to see electrons flying off the surface one at a time. And what that meant was that although yes, light behaves as a wave, but when light interacts with matter on an atomic scale, it behaves as a particle, because you don't get, what you get is just electrons being ejected one at a time, as if the light is interacting in small bundles with the electrons. And so this allowed, so Einstein proposed the idea that light can also behave as a particle, and a particle of light is what you see there, those little packets, and those are called photons.